Kaya nakakamiss ang office At least libre yung aircon. Sa bahay ka sa sari-sariling gastos. Okay, again, good afternoon and shout out to Anna, Jonathan, Charles, and Oriel. Thank you for joining me today. So last week we finished unit number 4. So now we will usher in a brand new unit for the course. So nasa unit 5 na tayo, the last unit for the course. Yay, malapit ang matapos. I guess we'll need at least 4 meetings to finish the course. So that means may natitira pa tayo siguro probably a couple of homeworks and then a final problem set, which probably I can give next week para uh, para medyo mahaba-haba yung time nyo to do it. Especially alam ko magsasabay-sabay na siguro last week or 2 weeks of classes. Sabay-sabay na dyan yung mga requirements ng iba't iba yung instructors. So maybe I can give our problem set in advance, even if we are not yet finished with its coverage. Anyway, tapos na naman natin siguro yung about 50% of the coverage because problem set 3 will cover unit unit 4 and unit 5. So para unti-unti nyo siya nagagawa, my target deadline for it would be on the 9th of June, the last day of classes. So medyo mahaba-haba para magkaroon kayo ng 2 or 3 weeks para matapos yung problem set. But do it paunti-unti para hindi kayo matabunan. That's the main reason why I'm thinking to give it in advance. And then after that, we'll have the final exam on the day the registrar will schedule us. Ang requirement ko lang naman doon ay isang term paper, reflection paper about your takeaways from this course. What did you realize? Ano yung mga important learnings na nakuha nyo? Kung meron man, hopefully meron para hindi sayang yung ating discussion every day. So, even though it's not a technical paper, I actually read it in details. So please be as specific and as comprehensive as possible because I actually give grades and deductions for the term paper, right? So hindi siya basta nagpasa perfect na kagad. So it's 10% of your grade, so it's still substantial. 10% nga ba, if I'm not mistaken, 10% nga. So malaki siya. So talagang siniseryoso ko yung pag-grade ng term papers. And aside from the term paper, I'll release an evaluation form para makita how do you think about the development of the course, its content, and actually my performance in the class para ma-improve ko yung sarili ko and ma-improve ko yung course if ever I'll teach it in the succeeding semester. So I'll just ask you your honest opinion. Yun, pag nagpasa kayo, perfect agad na siguro 1 out of 10. So yung ibibigay ko kasi 10% yung final project, yung final exam, siguro 1 point doon ay magagaling dun sa evaluation. The 9 points will be coming from the term paper that you will submit. So malaki yun, 1% sa final grade. So you should also submit that, okay? All right, so I also hope you already seen homework number 6. It's already posted in Canvas. The deadline I set was May 19th, pero kanina may nag-request. Actually, napilitan silang mag-request na extend sa May 20 kasi in-open up ko na pwede ko siyang i-postpone yung deadline to May 20 kung may magre-request. Pero ang problema sa akin pa rin nanggaling yung push to move it. Naalala ko lang kayo. Pero I hope sa mga susunod, sa inyo naman manggaling kasi sa face-to-face classes, ang hilig mangansyaw ng mga students na, sir, extend ng deadline. Pero hindi ko alam, bakit sa online ay hindi kayo nagre-request? Either nahihiya or kayang-kaya nyo naman siyang gawin kasi ang dami yung oras, quote-unquote, sa online setup. So, hindi ko lang talaga mapigilan yung sarili ko na i-offer na i-extend siya. Pero ideally, dapat sana sa inyo nanggagaling. So, inassume ko na lang na nahihiya kayo. So, ganun na lang. I'll extend the deadline to the 20th. But if you are already done with it and ready na kayo to submit it early, okay? I also need to apologize because my grading of homeworks 4 and 5 were a bit delayed. Na-realize ko siya nung binabasa ko yung mga sagot nyo dun sa problem 2 dun sa kumusta. I mostly replied dun sa mga election anxieties, yung mga hopeful messages kasi week before election pa yata yung kumusta question ko ano. Tapos unfortunately nagradean ko lang siya over the weekend. So doon ko pala na-replyan medyo antedated na yung replies ko but hopefully you still get the message and the replies, okay? So I appreciate all your sharing there. Para lang mapagaan yung mood and a little bit makilala ko kayo even if hindi ko kayo kilala sa mukha nyo. Ano? So at least meron akong konting alam at feeling ko kilala ko na kayo beyond dun sa mga avatars o actually hindi nga avatars eh. Kahit picture ayun yung maglagay sa Teams. Nakikita ko lang yung mga initials nyo. So hopefully, para naman pag nakita-kita tayo face to face, hopefully sometime next year or next acad year, ay makikilala ko kayo. Ano? So Charles, dahil dyan, +5 ka na. Joke lang. Thank you, Charles, for the kind words. Okay, so on a serious note, let's go back to what we'll need to discuss today. So sisimulan natin yung konsepto ng integration. Okay, so this is the third pillar of calculus na pag-aaralan natin. Actually, sa tatlong bagay lang naman talaga umiikot ang calculus: limits, derivatives, and integrals. Okay, so once you master those basic elements, parang avatar lang. So you will be able to understand the other specific streams ng calculus, yung functional analysis, optimization, etc. So they will always boil down to taking limits, derivatives, and integrals. Now, unlike the concept of limits, tapos mas akin nga dun sa konsepto ng derivatives, hindi ganun kalayo yung deviation na gagawin natin dun sa Math 36 development ng integrals dun sa gagawin natin ngayon sa Math 155. Siguro it's somewhere in the middle kasi yung limiting process medyo napakalayo dun sa Math 36 notion natin ng limits kasi mas generic siya. Tapos dumaan tayo or nagka-capitalize tayo about knowledge of limits of sequences para ma-prove yung mga konsepto ng limits of functions of a real variable. Okay? Dun sa derivatives, sobrang pahapyaw lang kasi yung definition niya, yun yung limit ng difference quotient na yun din naman yung ginamit nyo sa Math 36. Okay? Now, sa atin dito ngayon, sa development natin ng integral sa Math 155, hindi siya eksakto kung paano natin ginawa sa Math 36 yung integration. I mean, kasi sa Math 36, I imagine you took the limit of the Riemann sum. So, ang ginawa nyo, kinuha nyo yung limit ng summation ng areas ng rectangles, okay? As the number of rectangles increases without bounds, right? So you take a measurement of n rectangles, you sum up the areas of those n rectangles, and then you take the limit as the number of rectangles used increases without bounds. Yun yung ginawa natin sa 30 series, right? Sa Math 155, medyo iiwasan natin yon kasi hindi tayo masyadong nag-discuss about how to compute infinite limits, okay? Or pwede naman natin siyang tingnan ng sequences pero magiging medyo synthetic siya kasi ang kukunin natin ay limit ng sequence ng mga sums. So which can make our our development a little bit more complex than it should be. So gagawin natin yan, mas papasimplihin natin ng konti. And along the way ng pagpapasimple ng development na ito, mas i-generalize natin siya. Because if I remember it right, sa Math 36, dinefine lang natin yung integral in terms of continuous functions. Okay? Or may bonus sa dulo siguro after we discuss the properties of integrals ng Math 36, tinignan natin paano mag-compute ng definite integral ng mga functions ng by points of discontinuity. Now in Math 155, from the get-go, we will design this to be as generic as possible. Hindi lang para sa mga continuous functions, okay? Pero siguro sa mga bounded functions ang gagawin natin. So if it is bounded, then that means your function does not necessarily need to be continuous. Basta meron siyang bounded, kaya nating pag-usapan yung integration. Of course, there are more generic treatments of integrals which will allow for the integrals of unbounded functions, but that would be for a more advanced class na lang. So, titingnan natin ngayon yung pinaka-basic or pinaka-generic na definition ng integrals insofar as bounded functions are concerned. Kasi yung pagkakaroon ng integral para sa mga unbounded functions, siguro mas properly defined sila pag pumunta tayo sa Lebesgue integration. So ngayon, mas confined tayo sa Riemann integration. So kasi yung Lebesgue integral, sila yung mas general na klase ng integral. Yung Riemann integral, yun yung natutunan natin from Math 36. And most interesting functions ay Riemann integrable. Siguro may mga specific cases lamang na siguro ginagamit sa engineering o mga made-up abstract functions na Lebesgue integrable at interesting siyang tingnan. Pero para sa atin siguro kontento na tayo ngayon muna sa Riemann integrability or Riemann integrable functions. So please get a copy of Unit 5 lecture notes. So wala pa akong binabago though when I was discussing it in class kanina, medyo may mga corrections pa ako nakita. So kindly take note sa mga kopya na hawak nyo ngayon. So Unit 5 will be comprised of 4 sections. Probably will need at least one session for each section. So in section 1, we'll start with defining Riemann integrability. Kailan, ano ang Riemann integral? Kailan nagiging Riemann integrable ang isang function? So dito, kailangan nating i-build up yung definition from the ground up. So mula sa pinaka-basic, unti-untiin natin hanggang makarating tayo kung kailan Riemann integrable. Then we will see that the definition of being Riemann integrable is quite hard to utilize for practical purposes, like checking whether a function is Riemann integrable or finding what the Riemann integral is. So sa section 2, magde-develop tayo ng integrability criteria. Siguro, ano yung mga sufficient conditions para magkaroon siya ng Riemann integral? Halimbawa, kapag ang isang function ay continuous sa isang closed interval AB, malalaman natin na automatically integrable na siya. Pero the converse is not true because not all Riemann integrable are continuous. There are discontinuous functions that are Riemann integrable, which might be foreign to you kasi sa Math 36 ang natutunan lang natin mag-integrate ng mga continuous functions. Okay? And then after establishing Riemann integrability, then it would be fine to talk about what are the properties of the Riemann integral. And most of them ay mga properties na nakita nyo na sa 36, like additivity ng Riemann integral, ano yung integral ng sum, integral ng difference, and so on. So doon natin siya titingnan. And we will culminate not just the unit, but the course by talking about what the fundamental theorem of calculus is about. So any calculus course will not be complete if we will not be able to mention or at least discuss in some details yung fundamental theorem ng calculus. Ito yung pinaka-star ng lahat ng mga theorem sa calculus because all other nice results will emanate or will owe their existence in one way or the other from the fundamental theorem of calculus. Okay? So if you're ready, napahaba na yung introduction ko, let's dive in and go to section number 1. Pause muna ako for 1 minute. Hold on, guys. Umatake talaga yung yung runny nose ko kapag ka nagla-klase. So anyway, sana pagka face-to-face hindi na ganito kasi nakakaya itsura ko kung ganun. So all right, so okay, going back. So let's start with the very first definition. Ito yung una nating kailangang konsepto para ma-define kung ano ang Riemann integral ng isang function. And we need the concept of partition inducers. So a set P, which actually is a finite ordered set, so specific yung ordering, dapat naka-increasing order siya. So yung ordered set P, starting from x0 until xn, which is a subset of AB, will be called a partition inducer of the closed interval AB if it is a subset of AB and naka-increasing order nga sila with x sub 0 being equal to A and x sub n equal to B. All right? Actually, variable yung n. So kayo yung magde-decide ilan ang elements ng partition inducer. Okay? So it's called a partition inducer because the numbers x0 to xn will subdivide the interval or will partition the interval AB into little subintervals. Okay? Sa mga mas maliliit na subintervals. So this will look like this. Okay? So meron kang A dito, meron kang B. Diyan natin gustong i-define kung ano yung Riemann integral. Okay? So para ma-define siya, ang gagawin ko, ipapartition ko to, hatiin ko to sa mga mas maliliit na subintervals, which is basically what you did in Math 36. Ano? So kaya lang ang requirement natin para maging partition inducer yung isang set x0 until xn, dapat yung A siya si x0, tapos si xn siya si B, tapos si x1 dapat mas malaki kay A, si x2 mas malaki kay x1, and so on. Actually, it's not a big deal yung pagiging ordered nila, pero kailangan ko siya para well-defined yung mga lengths, yung mga intervals na i-define ko mamaya. Kaya gusto ko naka-increasing order siya. So that the interval x sub 0 to x sub 1 is not contained or will not overlap with any other subintervals. So yun yung dahilan, yun yung tanging dahilan kung bakit gusto ko naka-increasing order yung mga x sub i's. And then I want x sub 0 to be equal to A and x sub n to be equal to B para ma-encompass natin yung buong closed interval AB. So yun yung dahilan kung bakit medyo picky ako sa pagkaka-define ng partition inducer. Okay? So the partition inducer actually, as the name suggests, will induce a partitioning or a subdivision of the closed interval AB into disjoint intervals. Actually, not necessarily disjoint, pero ang sinishare lang nila ay yung common boundary point x0 until xn. Okay? So tatawagin nating I1 yung first interval or first subinterval, which is basically x sub 0 to x sub 1. X2 will be the I2 will be the interval from x1 to x2 and so on. And then we will denote by delta x sub I the length of the ith subinterval. So ang notation natin para sa length ng isang interval I sub I ay absolute value ni I sub I. And actually, it's not hard to compute because the ith interval II is basically the interval from x sub I from x sub I minus 1 to x sub I. So ang length niya lamang ay eto. Okay? Kaya gusto ko naka-increasing sila para well-defined ito, para positive yung length. Okay? So tatawagin natin siyang delta x sub I kasi alam niyo naman ang delta parang ano siya, notation for change. So yung capital delta. So delta x sub I is the change in x. So basically it is the length from the left to the right endpoint of the sub interval. Okay? So I think yun yung sinasabi rito. Okay. So some quick examples. Consider the interval A 0, 2. So siya yung closed interval AB natin. Si P1 at saka si P2 ay parehong partition inducers, right? Because they both begin at 0 and they both end at 2 and all intermediate points are in increasing order. Okay? So ito yung nagpapakita na ang partition inducer posibleng iba-iba sila ng mga number of elements. So mas marami tong partition points. So probably mas maliit yung mga intervals involved. All right? Though hindi necessarily laging lahat, pero in general, yung average length ng mga sub-intervals induced by P2 will be less than the average of the lengths of the sub-intervals induced by P1. Okay? And then can some of you help me out? Why did the example say that P3 and P4 are not partition inducers? Okay, so I'm accepting volunteers, okay? So bakit si P3 at saka si P4 ay hindi partition inducers? Just give me one answer and then iba nyo ng classmate ang magsasabi. Si Ana nauna na sa P3, sabi ni Ana, hindi kasi increasing yung mga elements ni P3, right? So yeah, that's right because 1/2 came after 1. So pero magkakaproblema tayo doon kasi ang mangyayari doon, so 0, si 2, so ang first interval natin ay 0 to 1. There seems to be no problem about that, okay? Tapos kaya lang, yung susunod na interval ay 1 to 1/2 which doesn't make sense. And even if you want to make sense of it, nandito siya. So mag-overlap siya with the first interval I1. Okay? So ibig sabihin parang madodoble yung weight para dun sa interval 1/2 to 1. Kasi kasama na siya dun sa I1, makakasama pa siya sa kay I2 kung pagbabaligtarin man natin yung interval of consideration na yun. Okay? So that's one reason why I don't want partition inducers to not be in increasing order. So thank you, Anna. How about the others? Wanna try P4? Bakit yung P4 ay hindi partition inducer? Okay, great. Noriel, thank you. Sabi ni Noriel, hindi kasi elements is zero, which is supposed to be x sub zero. Ayun, humabol din si Jonathan. Okay, thank you guys for responding. Yun din. Kasi si P4, hindi siya nag-start kay zero. So, ibig sabihin, yung mga numbers from zero until 1 ay hindi na nakasali doon sa doon sa partitioning ng closed interval 0, 2. So, you can say that P4 is actually a partition inducer for the closed interval 1, 2. But it is not a partition inducer for the closed interval 0, 2 because we are not or will not be able to look at the behavior of the function f on the interval 0, 1, which is basically half of the closed interval 0, 2. Okay? So, yon yung partition inducer. So, I hope you get kung bakit ganito ko gustong i-discuss or i-define yung partition inducers. Now, the concept of partition inducers is very important because I will use them to define what the lower and the upper Riemann sum are. Okay? So, yun yung nasa definition 5.2. So, dito nga lang sa definition, dinrap na yung Riemann. Okay? But I would like to call it the upper and the lower Riemann sum just to distinguish it from other type of integrals later. Pero sa 155 nga naman, isang klaseng integral lamang yung ating pag-uusapan. So probably that's why the name Riemann was dropped from the sum. Okay? Pero ganito yung mangyayari. Okay? So ang upper sum ni F relative to a partition inducer P. So ibig sabihin, yung upper sum ay nakadepende sa dalawang bagay. Nakadepende siya dun sa function na pinag-aaralan mo at saka dun sa partition inducer na kinoconsider mo. Alright? So dependent siya sa specific partition inducer. Now, how do we get the upper Riemann sum? We just need to get the summation of the quantity capital M sub I times delta X sub I. But we know delta X sub I is the length of the ith subinterval. Okay? And then M sub I is basically the supremum function value over the subintervals. Okay? So graphically, we can represent it this way. So let's go back to our partition inducer here. Let me just erase this, guys. Okay? So halimbawa, ito yung function f natin on the interval AB. Now, ang sinasabi ng partition ng upper Riemann sum, ganito yung gagawin natin. So, tingnan natin si x sub yung bawat subinterval. So, let's begin with the first subinterval, say I1. So, si x sub 0 to x sub 1. So, we are here. Yung multiplier na nandun sa loob ng summation ay delta x sub I. So, siya si delta x sub 1, which is basically the width netong interval neto. Tapos, yung multiplier sa kanya ay si big M sub I. So big M sub 1 actually is the supremum value of the function on the first subinterval. Yung pinakamataas na function value. Actually, technically, hindi pinakamataas na function value pero yung least upper bound ng lahat ng mga function values dun sa interval. Okay? In that particular case, this is the smallest possible upper bound. Tapos kukunin natin ito. Okay? Tapos, pag kinuha natin yung, ito yung si big M sub 1, pag kinuha natin si big M sub 1 times delta x sub m, delta sub x1, that is basically the area of this rectangle. All right? Which will ring some bells for you guys because this is exactly, matatandaan nyo, ganito po namin ginawa yung konsepto ng integral sa Math 36. Nag-consider kami ng mga rectangles, kinuha namin yung area ng bawat rectangle sa bawat subintervals. We took the sum and then we took the limit nung sum ng mga areas as the number of rectangles considered increases without bounds. So ganun din yung idea natin dito, no? Sa upper Riemann sum nga lang, kinukuha natin yung pinakamalaking or pinakamatangkad na posibleng rectangle sa bawat subinterval. Okay? So, if you have a specific or a fixed partition inducer P, kunin mo lang yung sum ng mga tallest rectangles that can be defined on each of the subinterval, then you're gonna get the upper Riemann sum. Okay? And then analogously, if instead of looking at the tallest possible rectangle on every subinterval, pinalitan mo siya ng shortest rectangle possible, so you're using M sub I to be the height. What is little m sub I? This is the infimum of the function value on the ith subinterval. Then what you'll get is the lower Riemann sum of F with respect to P. Okay, hold on guys. So yan yung konsepto natin ng lower at saka upper Riemann sum. Now, it is easy to see or to accept that the upper Riemann sum ay laging mas malaki sa lower Riemann sum provided you are considering the same partition P. Kasi nga sa upper Riemann sum, ang kino-consider mo yung tallest rectangle sa bawat subinterval. Tapos, if we will draw the shortest possible rectangles on the same subintervals, then definitely yung sum ng mga mas maliliit na rectangles. So for instance, for M1, ito yung M sub I, okay? Ito yung rectangle na i-consider natin. So yung bawat addend na makikita nyo dun sa summation para sa lower Riemann sum ay mas maliit kesa dun sa bawat addend na nandun sa upper Riemann sum. Or I mean pairwise, mas malaki yung nasa upper kesa dun sa nasa lower Riemann sum. So bawat addend dun sa lower Riemann sum ay mas maliit kesa bawat addend sa the corresponding addend niya sa upper Riemann sum, then we can say for certain that relative to the same partition inducer P, the upper Riemann sum is always greater than or equal to the lower Riemann sum. Okay? And then also, if F is continuous on the closed interval AB, then it will be continuous on each of the subintervals because they are closed interval, kung continuous si F sa buong interval AB, continuous din siya sa closed interval x0 to x1. And since the closed interval x0 to x1, yan ay compact, so by the extreme value theorem, ibig sabihin na-attain ni F yung kanyang maximum at minimum doon sa interval x0 to x1. So therefore, there is an x doon sa interval x0 and x1 kung kailan nagmi-minimum at nagma-maximum si function f. So therefore, instead of using the supremum and the infimum, kapag continuous si function f, then si m sabay siya lang yung maximum at si little m siya lamang yung minimum. Okay? So you might be thinking, parang halos magkaparehas naman yung minimum at saka infimum, tas maximum at saka supremum. But I hope you can now draw the line between those two guys. Ano yung pagkakaiba ng supremum at infimum? For nice functions, they will coincide with each other. Pero magkaiba sila kasi, or theoretically magkaiba sila kasi yung minimum siya yung pinakamaliit na posibleng function value. Pero yung infimum, siya yung greatest lower bound. Yung infimum hindi necessarily function value. Siya lang yung pinakamalaking lower bound para sa lahat ng mga function values. Yung minimum naman, siya talaga dapat yung pinakamaliit na function value. So function value siya muna, tapos kukunin mo yung pinakamaliit na function value. Okay? Pero for most cases, they will just coincide with each other. Pero yun nga, siguro dapat kasama to dun sa reflection paper nyo na, sir, natutunan ko yung pinagkaiba ng maximum at saka supremum and so on. Okay? Now let's look at a specific example, pagko-compute ng upper at saka lower Riemann sum. Okay? So in this particular case, we will revisit the closed interval 0 to 2 and consider the quadratic function x squared over this interval and the partition inducer 0, 1/2, 1, and 2. Okay? So clearly, this is a partition inducer kasi nahati niya yung closed interval 0 to 2 into 3 subintervals, namely si 0 to 1/2, si 1/2 to 1, tapos si 1 to 2. Ang length ni I1 ay 1/2, length ni I2 ay 1/2 din, length ni I3 ay 1. So hindi kailangan unique yung haba ng mga nandun sa partition inducer. Okay? Tapos, pag kukunin natin yung lower Riemann sum, alam natin na dapat kukunin ko yung infimum ng function values over the 3 subintervals. But since f is continuous on the closed interval 0, 2, so it is continuous on each of the 3 subintervals. Tapos yung bawat isa dun sa tatlong subintervals na yun ay compact. So sabi ni EVT, yung infimum ay equal sa minimum, tapos yung supremum ay equal sa maximum. Okay? So that means titingnan lang natin kailan nagiging minimum yung function value. But we know that x squared is an increasing function whenever the input is a non-negative real number. So yung minimum kay I1 ay nagaganap dun sa pinakamaliit na posibleng x value. Pinakamaliit na x value ay 0. So we know since x squared is increasing on this interval, so ibig sabihin ang pinakamaliit na function value ay si 0 squared. So siya si little m1, tapos times the length of I1, so 1/2. Kay I2, ganun din. Pinakamaliit na function value nangyayari kay 1/2. That will translate to 1/4 times the length of the interval, 1/2. Okay? And lastly, ganun din kay I3. 1 yung pinakamaliit na function value because that's going to be 1 squared. And then the length of the interval is 1, so we get this. And then, pag ginawa niyo yung arithmetic, you'll get that the lower Riemann sum is equal to 9/8. Just a disclaimer, if you're using a different partition inducer, then it's possible that you will get a different lower Riemann sum. Kasi nga yung lower Riemann sum, nakadepende siya dun sa partition inducer na pinili mo for your specific function. Okay? And then you can reverse the arguments para makuha yung upper Riemann sum. You can just say na, ang interest ko naman ngayon ay yung function value dun sa right endpoint ng bawat subinterval because the supremum, which turns to be the maximum function value, will always leave on the right endpoint, or on the right endpoints being the highest possible x values and the fact that x squared is increasing. Okay? So performing the same analogous calculations will give us an upper Riemann sum equal to 37/8. Okay? So questions about those things? I hope everything is clear. All right, thank you, Charles. So now let's jump. So, okay, sir, ayan na, meron na tayong partition inducer. Kaya pala kailangan ng partition inducer ay para ma-define ang upper saka lower Riemann sum. Sir, para saan yung upper at saka lower Riemann sum? Well, the answer, para ma-define natin yung lower at saka upper Riemann integral. Okay? Definition 5.3 tells us na kapag ka si f ay bounded. The reason that I want to talk about bounded sets ay para sure ako na nag-exist yung supremum at infimum. Because remember, sa pagkaka-define ng upper at saka Riemann sum, we need to take the infimum and the supremum of the function values over the subintervals. And there would be some problems if there is a subinterval on which our function is not bounded. Kung hindi siya bounded, so ibig sabihin hindi mag-exist si capital M at saka si little m para sa at least isa sa mga subintervals na nandun sa partition. Okay? So kaya kailangan ko bounded. Yung bounded sa isang closed interval, no? Pero meron kasi mga functions na hindi continuous pero bounded. So pipiliin ko na lang ay boundedness. Because if f is bounded on a closed interval, then it would be bounded on each of the subintervals. Then by the least upper bound property, dahil meron kang upper bound sa closed interval na yon, then magkakaroon ka na ng least upper bound. Kaya sufficient na maging bounded yung function f. Okay? So, kung bounded yung function mo, ano ngayon yung upper Riemann integral? Well, the upper Riemann integral will be defined to be the infimum ng lahat ng posibleng upper Riemann sum over all partition inducers. There's a typo here, so kindly mark your modules or your lecture notes. Dapat ito ay hindi curly P. So usual P lang to dapat. Kasi ang gagawin mo, para makuha yung upper Riemann sum, kukuhanin mo lahat ng posibleng partition inducer. And there would be uncountably infinite many of them. Tama ba? Uncountably infinitely many. Parang daming li. Basta magiging meron kang uncountably infinite number of possible partition inducers. Tapos hindi pa rin matatapos. Ano? Kukolektahin mo lahat ng posibleng partition inducer, tapos kukomputin mo lahat ng upper Riemann sum na nandun sa lahat, para sa lahat ng posibleng partition inducer. So tapos, pag na-compute mo na lahat ng posibleng upper Riemann sum, kukunin mo yung greatest lower bound among all those upper Riemann sums. And you see how tedious and complicated finding the upper Riemann integral is. Kaya kailangan natin talaga ng necessary or sufficient conditions para sa Riemann integrability. Para mas mapadali natin yung pagko-compute ng upper Riemann integral. Okay? So yun yung dahilan. So yun yung definition ng upper Riemann integral. Ito yung notation natin. So yung usual integral symbol over the closed interval AB, then you have your function f. Tapos wag na nating isama yung dx or dy kasi clear naman na isang variable lang naman kung saan tayo nag-i-integrate. Sabi niya, sir, nagagalit yung teacher ko ng 36 pag walang dx, pag walang differential yung integral ko. Ano? Bakit ngayon pumapayag na tayo? Well, yun ay dahil sa pagkaka-define natin. Sa Math 36 kasi, dinefine niyo yung dx to be a quantity. This is the differential of the independent variable. Tapos ito ay equal sa delta x, alright, sa length sa bawat intervals. Tapos ang ginagawa nyo kasi sa 36, kinukuha nyo yung limit ng delta, limit ng Riemann sum as delta x approaches 0. So importante talaga yung dx o yung delta x dun sa integral. Ngayon, wala namang variable tayong pinag-uusapan. Tinitingnan lang natin yung supremum ng mga function values over the subintervals. So without any regard to what dx or delta x is, so nakatago na siya dun sa pagko-compute ng Riemann at ng Riemann sums, ng lower at saka upper Riemann sum. Kaya ngayon, okay, relax na tayo. Hindi nyo na kailangang isulat yung dx. Ano? So this is our notation for the upper Riemann integral. On the other hand, to find the lower integral of f, then we will use this notation. Okay? So, nasa ilalim naman yung bar para masabi na siya yung lower Riemann integral. At para naman ma-compute yung lower Riemann integral, babalikan natin lahat ng posibleng partition inducer, kukomputin natin lahat ng posibleng lower Riemann sum. Once we have computed them, kukunin natin yung yung least upper bound. Kukunin natin yung supremum ng lahat ng mga lower Riemann sums. Okay? And then finally, we will say that f is Riemann integrable on the closed interval AB if and only if the lower and the upper Riemann integrals are equal to each other. And if f is Riemann integrable, then we will assign the common value of the lower and the Riemann integral to be the Riemann integral of the function f. Okay? So just be careful, merong crisscrossing na nagaganap dito sa definition ng upper at saka lower integral. Tingnan niyo sa upper integral. Kukunin natin yung upper sums. Tapos remember sa upper sums, ang kinukuha natin na height ng bawat rectangle ay yung supremum function value. So kukunin mo yung supremum function value para makuha mo yung upper Riemann sum relative to a partition inducer P. Tapos pag nakuha mo na yon, kukunin mo naman yung infimum. So parang papaliitin mo sila. Kabaligtaran yung sa lower. Sa lower Riemann integral. Sa lower Riemann integral naman, dun sa, kailangan mo yung lower Riemann sum. So lower Riemann sum, kinukuha natin yung infimum ng mga function values. Pag kinuha mo na yung mga infimum, kinuha mo na yung summation, kinuha mo lahat ng posibleng lower Riemann sum, saka mo kukunin yung supremum. Tapos, kahit supremum yan, tatawagin ko siyang lower. So parang hindi siya nagme-make sense, ano? Kasi may criss-crossing nga ng infimum at saka supremum dun sa definitions nila. Pero if you think of it, it makes sense. Kasi, ang gusto nating mga Riemann integrable functions ay parehas yung lower at saka upper Riemann integral. Kasi parang ganito yung idea. Alam natin na yung lower integral ni f relative to, say, partition inducer P1 ay mas maliit dun sa upper Riemann integral with respect to P1. Tapos, kung meron ka pang isang partition inducer, nandito yung kanya, halimbawa, P2, nandito naman yung kanyang upper Riemann sum. Mas malaki pa rin. Nasa kanan ng lower Riemann sum, lagi yung upper Riemann sum. Okay? Tapos, ang idea, kung siya ay Riemann integrable, dapat magkukumpul-kumpulan sa gitna etong lahat ng lower at saka upper Riemann integral niya. Kaya ang criteria natin, dinefine natin to be the upper Riemann integral ay yung greatest lower bound ng mga upper Riemann sum. Para ma-drive sila, yung mga upper Riemann sum, ma-drive sila pakaliwa para pumunta siya somewhere in the middle. Tapos, para may chance na ma-meet ng mga lower Riemann integral, yung mga upper Riemann integral, ang gagawin natin, kukunin natin yung least upper bound. Kukunin natin yung pinakamaliit na mas malaki sa lahat ng mga lower Riemann sums. Tapos yun yung tatawagin natin na lower integral. And the goal is that they will meet in the middle. And this middle thing here is what we will call the integral of f over the interval AB. Okay? So kaya pag nalito kayo, bakit saan nga lalagay yung supremum? Saan lalagay yung supremum? Pwedeng i-drawing nyo itong illustration na to. Para makita nyo, kaya pala upper bound ng mga lower sums yung titingnan ko. Kukunin ko yung least upper bound para ma-drive siya na lumaki siya ng konti para lumapit siya doon sa pinakamalaking lower bound naman ng mga upper Riemann sums. Okay? So yun yung idea ng Riemann integrability. Okay? Are you sold with the definition? Even though, sabi nga ni Charles, Math 30 series left the convo. Okay, dahil walang nagiging violent sa chat, sa reaction siguro. Yeah, thank you, Charles. Nakakasunod pa naman daw. Okay, so bigyan natin ng ilang concrete examples, okay? Though, sabi ko nga, ang hirap gamitin itong definition na ito. Kasi ang laki ng burden. Burden ay i-consider natin lahat ng posibleng partition inducers, but there would be uncountably many possible partition inducers. Tapos, kukunin ko pa yung suprema at saka infima sa bawat subintervals para lang makapag-compute ng isang lower at isang upper Riemann sum. Pero para mahanap yung lower at saka upper Riemann integral, kailangan kuna ng supremum at infimum yung mga sums na yon respectively. So that will create a lot of problems, especially for complicated functions f. All right? Pero dahil gusto lang nating makita in action yung definitions, tingnan natin yung mga specific simple functions. Umpisa natin sa dito. Oops, hindi pala ako naka-pointer. Doon sa constant function. Now, this example claims that any constant function is integrable on any closed interval AB. Madali lang itong gawin kasi constant yung function. Na-imagine nyo na, constant yung function sa interval AB. So, ibig sabihin yung maximum at minimum ay madaling makompute. Yung maximum at minimum or the infimum and max and supremum on different subintervals will just be equal to the constant value. Okay? And that will happen kahit ano pang partitioning ng AB yung gamitin ko. Okay? So in particular, if we consider a random or an arbitrary partition inducer P of AB, partition inducer yan ni AB, then sa kahit anong subinterval, okay, kahit ano pa yung partition inducer, yung infimum na mga function values, yung little m sabay, ay equal lamang kay C. Kasi nga, constant lang yung value. Ganun din yung mangyayari dun sa suprema. Yung lahat ng suprema ay equal lang kay C. Kahit ano pang partition inducer yan. Kahit pang ilang subinterval pa yan sa kahit anong partition inducer. Okay? Tapos si C ay independent ng I, so pwede siyang lumabas ng summation. And that will bring us to these two quantities over here. Now, what is delta x sabay ulit? Delta x sabay ay yung haba ng ith subinterval. When we sum up the lengths of all the n subintervals that we have considered, okay, ibig sabihin nabuo na natin yung buong interval AB. So yung summation ng mga lengths ng mga subintervals will just simplify to b minus a. And that is the reason why we want, or that's another reason why we want x sub 0 to be equal to a and x sub n to be equal to b. Para yung summation ng lengths ng lahat ng subintervals ay magiging equal kay b minus a. So this guy will be b minus a, this guy will be b minus a. So any lower Riemann sum and any upper Riemann sum will be equal to b minus a. So the infimum ng mga upper sums ay equal dun sa common value. yung supremum ng mga lower sums ay equal doon sa common value na c times b minus a. Therefore, the upper and the lower Riemann sums are both equal to c times b minus a. And since those two are equal, then we can say that the function f is Riemann integrable, and not just that, the Riemann integral is equal to the common value c times b minus a. Right? End of solution. Okay? Tapos alam nyo naman, kaya nyo naman itong i-check, no? Yan yung integral talaga ng c from a to b kung gagamitin niyo yung mga theorems mula sa Math 36. Okay? So this is probably not too much interesting for you guys because you already know this from Math 36. Tumingin tayo ng isang mas interesting na example. So ito yung mas exciting na part. Ano, i-consider natin yung Dirichlet function. I think we met the Dirichlet function earlier in the course. Recall lang natin ano yung Dirichlet function. Ito yung characteristic function ni Q doon sa closed interval 0, 1. Because if you are a rational number on the closed interval 0, 1, then your value under the Dirichlet function is 1. Tapos kung hindi ka naman rational, ang function value mo sa Dirichlet ay equal kay 0. Okay? And this is a function that is not continuous. Okay? It is actually not continuous anywhere on the closed interval 0, 1. And that is owed to the fact that Q and Q complement are both dense in R. All right? So kaya hindi siya nagiging continuous anywhere. Kasi ang bilis ng pagbabago ng function value, you could be 1 at a particular point, and right after, hindi ka pa nakakagalaw, konti pa lang yung galaw mo, 0 na kagad yung function value. Because between any two real numbers, there exists an irrational number and vice versa. Okay? Kaya hindi to continuous everywhere. Tapos kung nag-stick tayo sa Math 36 definition or development ng integral, imposible na to kagad magkaroon ng integral. Okay? Pero ngayon, posible. Kasama siya dun sa definition natin kasi bounded si f. It's bounded above by 1 and bounded below by 0. So we can define what the lower and the Riemann integral are. Okay? Pero ibang usapan kung Riemann integrable nga siya. Okay? So now, let's see. Let's check. Now, we can consider any partition inducer P of 0, 1. Okay? So kahit ano yan, arbitrary or random partition inducer. Ito ay 0, ito ay si 1, meron tayong x1, x2, x3, hanggang makarating tayo dito kay xn. Okay, random yan. Tapos, para makuha yung upper Riemann sum, okay, over with respect to this partition inducer, we need to get the suprema of the function f on all of the subintervals para makuha natin yung big M sabay. Okay? So, tingnan natin. From x sub 0 to x sub 1, ano yung maximum function value? Okay? May dalawa lang tayong options kasi dalawa lang naman yung function value na ina-assume ng function natin. It's either 1 or 0. Okay? Pero na-attain ba ni Dirichlet function yung value na 1 doon sa closed interval x0 to x1? Any thoughts? Probably aside muna kay Anna and yung mga sumagot na kanina. So I think that leaves me with only one other person. Tama ba? Si Noriel, okay na rin si Jonathan. Charles, time to shine mo na. Bakit ako sure na ang supremum dito ay equal kay 1? Kasi bakit ako sure na there is a point in this closed interval 0, x0 to x1 na ang function value ni f ay equal kay 1. Sure ako, somewhere in this interval, nagiging 1 yung function value. Why is that so? Any hula? Unahin ko si Charles kasi siya yung wala pang bonus points for today. Not to pressure you guys, baka hindi na kayo umattend next lecture session. 4 na nga lang kayong uma-attend, baka hindi pa kayo umattend next time. Okay, thank you, Charles. That's a nice answer. Sabi niya kasi between irrationals ay may rational. Which makes the function value equal to 1. Great, that's correct, Charles. Medyo let me tweak your argument a little bit kasi hindi ako sure na si x0 at saka si x1 ay mga irrationals. Ang alam ko lang sila ay real numbers. But the way we stated the density property of Q complement or the density property of Q ay between any real number. Alright? So medyo i-edit ko ng konti yung sagot mo, Charles. Ang gusto kong sabihin dito ay, oh, si x0 at saka si x1 parehas silang real numbers. Alam ko by the density property of Q in R, sa pagitan ng dalawang rational number, sa pagitan ng dalawang real number, sure ako may nagtatago dyan na isang rational number. At dahil meron diyang isang rational number, at least isang rational number, sa closed interval x0 to x1, ang supremum function value on that closed interval will be equal to 1. And that will be true for all of the other subintervals. So that means big M sub I is always equal to 1. Alright? Tapos, so mawawala na itong multiplier na yan, wala na siyang effect dun sa summation, dun sa product. So basically, this will just be the summation of the lengths of the intervals, all right? And since the closed interval 0, 1 has length 1, so the sum of delta x sub I is equal to 1. And that would be the value of any upper Riemann sum. Okay? Lahat ng posibleng upper Riemann sum, ang value lang lagi ay 1. If we take the infimum ng mga upper Riemann sums, equal yun kay 1. So we can conclude from here that the upper Riemann integral of f over the closed interval AB is equal to 1. Now, if we want f, the Dirichlet function, to be Riemann integrable, then we pray na yung lower Riemann integral ay dapat equal rin kay 1. However, mabibigo tayo rito kasi in an analogous argument as what Charles pointed out earlier, si x dense din naman ang Q complement sa R. So sa pagitan ng dalawang real numbers, laging diyang may nagtatago na at least isang irrational. At dahil meron diyang isang irrational number, alam ko na there is at least one point between x0 and x1 when the Dirichlet function zeroes out. Dahil nag-zero na yung Dirichlet function sa at least isa, sa isang point doon sa first interval, so ibig sabihin sa first interval na yon yung minimum o yung infimum ay equal kay 0. And then the density property of Q complement will also apply to any other subinterval. And it doesn't matter how we create the subintervals, ganun lagi yung makukuha natin. So yung little m sub I ay laging equal kay 0 regardless of which subinterval we are on, and also regardless of how we partition the closed interval 0 to 1. So that means in any case, the lower Riemann sum will always be equal to 0. And when we get the supremum ng mga zeros, ang lagi lang nating makukuha ay 0. So that means the lower Riemann integral of f is equal to 0, and the two guys are not equal to each other. So therefore, we conclude that sadly, the Dirichlet function is not Riemann integrable. Okay? But at least now, medyo kampante tayo or medyo mas comfortable kasi si Dirichlet function, napakasimple niya eh. Isa lang siyang function na either 0 or 1. Okay? Sa Math 36, hindi na tayo papayag na pag-usapan kahit lower Riemann integral or upper Riemann integral kasi nowhere continuous nga itong function f. Pero at least now, for this very simple bounded function, meron tayong konsepto ng check kung siya ay Riemann integrable or hindi. Okay? So is that clear? Is checking Riemann integrability now makes more sense? Teka, baka mamatay yung Teams ko. Lowbat na si laptop. Okay. I hope everything's fine. Wala naman nagre-react, so I'll move on. Okay. Now, what we'll do next is to look at a series of lemmatas or lemmas. Depende kung anong gusto nyong plural ng lemma. Okay, ang mga results na gearing towards into establishing that the lower Riemann integral is always less than or equal to the upper Riemann integral. So ito yung parang gusto kong end result. Okay. Now yung unang inequality ay madaling tanggapin. Kasi alam natin by definition, yung lower integral, ito ay supremum ng mga lower integrals, ng mga lower sums, right? By definition, the lower Riemann integral is the supremum of all the lower sums. So ibig sabihin, kung siyang supremum, it is an upper bound in the first place. Supremum ay least upper bound. So yung lower Riemann integral ay upper bound ng lahat ng mga lower Riemann sums. So therefore, this inequality is true. Ganun din naman yung panghuling inequality. The upper Riemann integral is the infimum or the greatest lower bound of the upper Riemann integrals. So therefore, it is in the first place a lower bound. So ibig sabihin, itong upper Riemann integral ay mas maliit or equal sa lahat ng mga upper Riemann integrals. So basically, clear itong dalawang inequalities na yan. The question is this always true? Is the lower Riemann integral always less than or equal to the upper Riemann integral? Okay? Yun yung gusto nating i-establish sa mga sumusunod na lemma. Lemmas to dapat. Kasi hindi pa siya na-prove sa lemma 5.1. Okay? Now, sa lemma 5.1, kung i-assume natin na bounded si function f, and not just that, we will assume that m is the infimum, yung lower bound. Tawagin natin siyang infimum na kagad. Okay? Tapos kung meron nag-exist na upper bound, na least upper bound o supremum para kay f, then we know that the lower sum is always less than or equal to the upper Riemann sum, provided you are using the same partition inducer. Medyo may kasalanan pa daw kanina kasi dinrawing ko to kanina, sinabi ko na alam naman natin na ang least upper bound ay laging mas mali, lahat ng lower Riemann sum ay mas malaki sa kahit anong upper Riemann sum. Tinanggap nyo naman siya without proof kasi nagme-make sense, di ba? Or actually, baka nabanggit ko nga yung essence ng proof. Bakit yung lower Riemann sum ay laging mas maliit kesa sa upper Riemann sum if you're talking about the same partition inducer. Okay? So yun lang i-formalize ng lemma 5.1. Kasi anong sabi niya ngayon? Sinimulan niya rito. Yung infimum doon sa buong interval AB ay laging less than or equal to dun sa infimum sa bawat subinterval. Tapos, obviously, yung infimum sa bawat subinterval ay mas maliit or equal dun sa supremum dun sa subinterval na yon. Okay? Pero dahil ito ay supremum ng isang subinterval na parte lamang ng buong interval AB, then this supremum is less than or equal to the supremum all throughout the closed interval AB. Okay? So that's why this inequality is obvious. Okay? Any objections there? Okay, mukhang wala naman. Nag-make sense naman yung inequality. Okay. Then what I'll do next is to multiply all sides by delta x sub I. Delta x sub I is the length of the ith subinterval, so it's a actually it's a positive number, so the inequalities won't change. Tapos kukunin ko, dahil totoo ito sa lahat ng I, alright, pwede kong kunin yung summation ng lahat ng sides over all possible i's. Okay. Totoo pa rin yung inequality na may mga summation na kasi bawat isang addend, yung mga corresponding addend, yung ith addend ay laging mas maliit. Yung ith addend using little m sub I ay laging mas maliit dun sa ith addend dun naman sa involving capital M sub I. So ibig sabihin term by term mas malaki yung ina-add ko dun sa side na to kaysa sa side na to and so on. So ibig sabihin mai-inherit nung mga summation yung property ng inequality ng mga to. So that's why I can arrive at this guy. Okay? And then little m will go out because it's independent of I. Again, we'll be left with delta exaby, but we know that the sum of the delta exabytes will be equal to b minus a. So this guy will just be m times b minus a. And then this guy is the very definition of the lower Riemann sum relative to the partition inducer P. So this guy is essentially this one. Tapos ito naman, by definition, yan yung upper Riemann sum with respect to the partition P. And then finally, big M will come out of the integral of the summation of the lengths of the interval. So that's going to be b minus a. So hence the right-hand side or the rightmost side of that inequality will be equal to m times b minus a. Okay? And that establishes lemma 5.1. Nakita na natin ngayon na kapag ka nasa same partition inducer ka, truly, yung left Riemann sum ay laging not left, yung lower Riemann sum ay laging not to exceed the upper Riemann sum. And actually, there is a lower bound for both of them. Little m, the infimum over the entire interval times the length of the interval is the lower bound for this infimum. For this lower sum. And the supremum over the entire interval times the length b minus a is an upper bound for the upper Riemann sum. Okay? So yun yung unang result. Meron tayong 4 na lemmas para lang actually tatlong lemmas para ma-discern yung result kanina about the inequality with the upper and the lower Riemann sum, okay? Na magiging lemma 5.4 natin. Okay? So, kung tanggap niyo naman yung proof ng lemma 5.1, probably we can pause for a 1-minute break. Inom lang ako ng tubig. So, habang dinadigest or pinaprocess nyo yung mga naunang results. Medyo lumamig na ng konti dito sa amin, kumulimlim na. So, sana umulan ng malakas para pwedeng maligo sa ulan. Nakakamiss yung naliligo ka sa ulan or sa isang ilog habang umuulan, lumalaki yung tubig. Feeling mo nasa isa kang magandang swimming pool. Biglang nag-reminisce, Okay. Now, before we go to the second lemma, meron tayong isang bagong konsepto na i-define. Yun naman yung isang refinement ng isang partition. So, ang isang partition inducer P star ay tinatawag na refinement ng isa pang partition inducer P if P is a subset of P star. Okay? So, ang idea rito ay parang nagdagdag ka lang ng partition points kay P para mabuo si P star. Tapos ang tawag natin doon ay refinement. Na-refine natin yung partition inducer P by merely adding additional partition points. So ang idea, halimbawa ganito, meron kang partition inducer na x0 hanggang xin. Okay? So meron ka dyang x1, x2, x3, and so on. All right? So, pag nagdagdag ka ng kahit isang point on the appropriate place para maging partition inducer yung panibagong point, wala kang tatanggalin kay P. Magdadagdag ka lang. Tapos di ba yung partition inducer dapat ordered set na increasing order. Magsingit ka lang ng isa pang point, at least isa pang point dun sa partition inducer P, makakuha ka na ng isang refinement. Okay? Halimbawa rito, pwede ako magdagdag ng panibago. Halimbawa y1, magdadagdag ako dito ng panibago, y2, dagdag ako ng y3, y4, tapos, and so on. Kolektahin ko yung mga x's at saka yung mga y's into a set, order them properly, then I'll get a refinement ng partition inducer P. Bakit siya naging refinement? Kasi originally, yung first interval under the partition inducer P ay itong kulay yellow. Pero, dun sa refinement P star, makikita nyo, mas maliit na yung partition, yung first interval. Ito na lang siya, from A to Y1. So in a sense, we have a finer mesh. Mas maliliit na yung mga subintervals na kinoconsider. Which is actually not new to you. Ito yung ginawa nyo. Nirefine nyo ng nirefine yung mga rectangles nung nagagawa kayo ng Riemann sum sa Math 36 na gumagamit kayo ng mas mga mapapayat na mga rectangles para makuha yung Riemann sum. Tapos yung Riemann integral. Tapos kukunin niyo yung limit habang yung number of subintervals which in effect will require using thinner and thinner rectangles para makuha yung Riemann integral sa Math 36. So dito, ito yung refinement. Kaya pag meron kang superset ng isang partition inducer, nakakagawa ka ng mas pino na partitioning ng closed interval AB. Mas marami ka ng subintervals na theoretically mas maliit yung average lengths kesa dun sa original partition inducer. All right? So here's a quick example ng partition inducer. Okay? So parehas silang partition inducer. Now, the more interesting question is what will happen to the upper and the lower sum if we are using a refined partition? The answer is in lemma 5.2. It says that if P star is a refinement of P, then using P star will give us a larger lower Riemann sum and a smaller upper Riemann sum. So pagka nire-refine natin ng nire-refine yung partition inducer, mas lumalaki yung lower Riemann sum, pero mas lumiliit yung upper Riemann sum. Which makes sense kasi ang gusto natin mag-meet in the middle yung lower at saka upper Riemann sum. And Math 36 taught us na para magawa yun, kailangan lang nating panipisin yung mga subintervals, which basically translates to refining and refining our partition inducer over and over again. Okay? So now let's prove lemma 5.2. Okay. Now, medyo specific yung pagkaka-define ko ng partition, ng refinement ng partition P. So dito nag-start ako sa partition P or partition inducer P. Tapos, ang idea kasi ay, para makabuo ka ng partition inducer, katulad nung dinrawing ko kanina, ang paraan para essentially, pag nagre-refine ka ng partition, parang pinapartition mo uli yung mga sub-intervals, right? So meron tayong interval I1, which is A to X1. Nung nakagawa ako ng isang refinement, na breakdown na yung I1 into two smaller intervals. So basically, you can think of refining an interval or refining a partition inducer by further partitioning the closed intervals generated by the original partition inducer. Okay? Yun yung ginawa niya dito. Sinabi niya na kung meron akong refined partition inducer P star, pwede ko siyang tingnan as the union ng mga partitioning ng subintervals. Kaya tayo nagkakaroon ng partition inducer P star kasi yung isang subinterval yung isang subinterval x sub I minus 1 to x sub I ay hinahati ko pa sa iba't ibang partitions. Okay? So ito ay na-breakdown into more subintervals using the partition inducer P sub I star. So si P sub I star ay isang partition inducer. Siya ay nag-start kay x sub I minus 1. Tapos matatapos siya kay x sub I. Tapos meron ditong mga points in between written in increasing order. Okay? So kaya partition inducer si P sub I star pero noong subinterval x sub I minus 1 until x sub I. Importante ko siyang tingnan as a partition inducer kasi gagamitin ko si lemma 5.1. Kaya lang, gagamitin ko si lemma 5.1 in P sub I star considered as a partition inducer ng x sub I minus 1 to x sub I. Okay? So, ibig sabihin, ito yung inequality na makukuha ko from lemma 5.1. Yung lower Riemann sum relative to P sub I star ay less than or equal to sa upper Riemann sum relative to P sub I star. Tapos, silang dalawa ay bounded below by the infimum, right, on this interval times the length of this interval which basically is x sub I minus x sub I minus 1. Ganun din yung nangyari dito. So essentially, talagang in-apply ko lang yung lemma 5.1 doon sa specific partition inducer P sub I star nung isang subinterval. At dahil si P star I assume to be a refinement, lagi ko itong magagawa sa lahat ng mga refined subintervals under P star. Okay? So dahil totoo yan, and then I will also note that the summation nitong mga lower Riemann sums on the partitions on the ith subinterval, pag pinag-sum ko lang to or pinag-add ko lang lahat ng mga lower Riemann sums over the subintervals induced by the original partitioning, I will get the total lower sum with respect to P star, the refinement P star. Kasi itong bawat lower sum na to ay with respect lamang dito sa interval x sub I minus 1 hanggang x sub I. Kung gusto ko yung lower Riemann sum with respect to P star, which is a partitioning nung buong closed interval AB, kailangan pag-plus-plusin ko yung mga lower sums na nakuha ko sa bawat subintervals ni AB. Kaya naman, makukonclude ko ito. Yung lower Riemann sum ni F with respect to P star ay equal lamang dun sa summation ng lower Riemann sum ni F on the ith subinterval induced by P relative to Pi star. Tapos ganun din yung nasa upper Riemann sum. So basically, ang idea kasi, lalagyan ko to ng summation. Lalagyan ko yan ng summation. Etong nasa gitna pala, siya lang yung refinement nung siya yung lower Riemann sum ni F with respect to dun sa refinement. Tapos itong summation na to, saan equal tong summation na to na nasa kaliwa? Summation lang siya ng mi delta x sub I. So basically, this is the lower Riemann sum of F with respect to the original partition inducer P. And hence, we have shown that the lower Riemann sum prior to the refinement is less than or equal to the Riemann sum or the lower Riemann sum we get after the refinement. Tapos ganun din yung mangyayari dito. Alright? Kunin ko yung sum, makukuha ko yung upper Riemann sum with respect to the refinement. Tapos ito naman, by definition, ito lang yung upper Riemann sum with respect to the original partition inducer. So the refined upper Riemann sum is less than or equal to the unrefined upper Riemann sum. And hence, theorem 5.2 proven. It's a check. Okay. Okay. So medyo 4 minutes na lang yung natitira. Pero I hope you can lend me probably another 5 to 10 minutes para lang mahabol natin yung kabilang section. Because there, I was able to finish lemma 5.4. So tapusin lang natin. But interrupt me if you have any questions or if something is not making sense. Maikli na lamang yung proofs nito. Siguro total of 7 lines na lang yung kailangan natin gawin. So sa lemma 5.3 naman, medyo mas powerful itong result na to. Ano? Kasi yung lemma 5. Yung lemma 5.1, ang sabi niya, kapag ka meron akong isang fixed na partition inducer, yung lower Riemann sum ay understandably less than or equal to the upper Riemann sum with respect to the same partition inducer. No question about that. But lemma 5.3 is much more general because it is claiming na yung lower Riemann sum with respect to a partition P1 ay laging mas maliit sa kahit na anong upper Riemann sum, kahit magkaiba yung partition inducers nila. So never magkakaroon ng lower Riemann sum na mas malaki sa isang upper Riemann sum. Kasi kahit ano pa yung partition inducer na gamitin mo sa lower sum, lagi pa siyang mas maliit sa kahit na ano pang upper Riemann sum that would have come from any partition inducer. Okay. Actually, nung binabasa ko to, before reading the proof, napaisip ko talaga, napaka-powerful ng result na to ha. Kasi kahit anong partition inducer ang gamitin mo kay L, kahit gaano mo siya i-refine. 'Di ba pag nire-refine natin yung partition inducer L, laging lumalaki ng lumalaki yung yung lower Riemann sum. Sinasabi nito na kahit paano mo pa siya i-refine, hindi ka aabot kahit dun sa pinakamaliit na posibleng upper Riemann sum. Okay? Now, the proof actually is very ingenious. Napakagaling ng pagkaka-prove. Ginamit niya yung konsepto ng partition inducer. The very same result that I am thinking na pwede kong gamitin na i-disprove ito. Yung pa pala yung makakapag-prove nung lemma 5.3. Right? The clever trick is this. I will consider, kasi si P1 at saka si P2 ay arbitrary partition inducers. Walang relasyon si P1 at saka si P2. We don't know which is a subset of which has more elements, which has smaller elements, or whatnot. Basta sure tayo, kahit ano pa yan, lahat ng lower Riemann sum ay hindi lalaki sa lahat ng mga upper Riemann sum. Okay? So, may tanong si Charles. Just wondering lang po, pag ni-refine yung mga partitions. So, anong mangyari, Charles? So, ang mangyari lang doon, palaki ng palaki yung mga lower Riemann sums na makukuha mo, pero paliit ng paliit yung mga upper Riemann sums. Pero kahit paulit-ulitin mo pa yung refinement, kahit gugulin mo yung buong lifetime mo pag-refine, wala kang makikitang lower Riemann sum na mas malaki sa kahit na ano o kahit na gaano kaliit na upper Riemann sum. Yun yung sinasabi ng lemma 5.3. Okay. The ingenuity in the proof of lemma 5.3 comes here. Sinabi niya, si P1 union P2, sure ako refinement siya ni P1 at saka ni P2. Alright? Kasi mula kay P1, nagdagdag lang ako yung mga elements na nanggaling kay P2. So indeed, this is a refinement of P1. So dahil refinement siya ni P1, yung lower Riemann sum ni with respect to P1 ay less than or equal to dun sa lower Riemann sum with the refinement P1 union P2. Right? So ito, ginamit natin yung lemma 5.2. Pero, okay, gagamitin ko yung lemma 5.1 nang sinasabi ay yung lower Riemann sum sa isang fixed partition inducer ay mas maliit or equal sa upper Riemann sum with respect to the same partition inducer. So totoo itong inequality na to. Kasi yung lower Riemann sum with respect to P1 union P2 ay mas maliit sa upper Riemann sum with respect to P1 union P2. Okay? Pero ito, si P1 union P2, sinabi natin ay refinement siya ni P2. So ibig sabihin, mas lumiit or mas malaki actually yung upper Riemann sum before we refine P2 kesa dito sa refined upper Riemann sum. So therefore, this inequality will follow. Again, because P1 union P2 is a refinement of P2. Tas ginamit ko yung lemma 5.2. And in summary, we have shown that the lower Riemann sum with respect to P1, which is arbitrary, is less than or equal to the upper Riemann sum of F with respect to any arbitrary partition inducer. So never ka makakita ng lower Riemann sum na mas malaki sa kahit anong upper Riemann sum. Okay? That's lemma 5.3 for us. Tapos ngayon, ready na tayo para i-prove yung sinabi ko kanina before we look at the lemmas na hindi masyadong obvious na yung lower Riemann sum ay yung lower Riemann integral ay laging not to exceed the upper Riemann integral. Yun naman yung lemma 5.4. And again, there's a very ingenious proof to it. Okay? Tingnan natin yung proof niya. So nag-consider siya ng isang arbitrary partition inducer P nung closed interval AB. Okay. Tapos sabi ng lemma 5.3, okay, pag kumuha ako ng, yung lemma 5.3, yung lower Riemann sum with respect to the partition inducer P ay laging mas maliit sa kahit na anong upper Riemann sum. Kahit ano pa yung partition inducer P prime na gamitin ko. Okay? So this statement is telling us that this guy is a lower bound para sa lahat ng upper Riemann sums, mapaanong partition inducer pa yung gamitin. Okay? So lower bound siya nun, pero remember uh, the upper Riemann sum is actually the greatest lower bound ng lahat ng mga upper Riemann sums. Alright? So itong lower sum na to ay lower bound, pero yung upper Riemann integral siya na nga yung greatest lower bound. So this guy must be less than or equal to the upper Riemann integral. Okay? Does that make sense? Tapos ngayon, if you flip ko naman yung argument. Note that P is an arbitrary partition inducer, so this inequality is true sa kahit anong partition inducer. So this is telling us that the upper Riemann integral is an upper bound para sa lahat ng mga lower Riemann integral. Para sa lahat ng mga lower Riemann sum. Pero remember that the lower Riemann integral, ito yung supremum. Ito yung least upper bound para sa lahat ng mga lower Riemann sums. Pero sabi natin si upper integral, okay, ay isang upper bound para sa lahat ng mga lower Riemann sums. Pero alam na natin ang pinakamaliit na upper bound para sa mga lower sums ay yung upper integral. Okay? So that means this must be less than this guy. All right? So, yeah, and that establishes lemma 5.4. That the lower Riemann integral is always less than or equal to the upper Riemann integral. Okay? So basically, the implication of lemma 5.4 is that it suffices to show, so thus, it is sufficient to show that the upper Riemann integral is less than or equal to the lower Riemann integral to show that f is integrable. Okay? Kasi gusto natin sa integrability, dapat equal yung upper at saka yung lower Riemann integral. Pero alam na natin from lemma 5.4 that the lower Riemann integral is less than or equal to the upper Riemann integral. So, if you will be able to show that also, aside from this established fact, that for your specific function f, it so happened that the upper Riemann integral is less than or equal to the lower Riemann integral, then it follows that your function f is Riemann integrable. Actually, this guy could be a sufficient condition or is a criterion for Riemann integrability. Hindi na natin kailangan yung equality kasi sure na tayo dun sa isang inequality. Alright? Pag na-prove mo yung reverse inequality, magiging equal na yung dalawang Riemann integrals. Okay? So yun yung isang integrability criterion that we have right now. Now, this is still tedious to do. So next meeting, we'll look at some more integrability criteria. Okay? Ano yung mga sufficient condition para makonclude natin kaagad ng isang function ay Riemann integrable without necessarily going through the definition of the Riemann integrability nor going through the tedious work of establishing this one inequality over here. Okay? But that's gonna wait for Thursday, all right? So questions, guys? So I feel that there are no questions. So if that's the case, then we'll meet again on Thursday to look at the integrability criteria. But until then, guys, I hope you stay safe and mag-break din kayo sa paggagawa ng ACADS whenever you can. All right? Bye, everyone.